All right, so we're going to look at some physical properties of gases, and let's start by talking about pressure. Now, I kind of defined pressure or where it comes from in the last video. Basically, pressure of a gas comes from those molecules colliding with the walls of its container. But the mathematical definition of pressure is that it's the force of an object exerted over some area. So force over area. And we experience pressure every single day, every single second of being alive. There is some sort of pressure that the atmosphere, the gases in the atmosphere, are exerting on our bodies every second of every day. You can kind of see this from the first picture there. The atmosphere, the air molecules, and air is made up of nitrogen, oxygen, carbon dioxide, and some other minor gases. But those gas molecules are pushing down on us, and it exerts a pressure of about 14.7 pounds per square inch. And while we might not necessarily feel that when we're, say, at sea level or close to it, um, what happens when we go up to the mountains? So here's a great picture of some mountains. Maybe they're snow-capped. But if we go start here at sea level, this is us, and we're under a high amount of pressure. And then we go up to the mountains where there's much lower pressure. Our bodies experience this because we'll start to feel our ears pop. There's less gas there. And so that pressure in our ears is kind of released. And so that's why we get that experience of either of our ears popping. Either we go up to the mountains or we fly in a plane. There's less gas pressure up there. Now, the units of pressure, I should say the SI unit, is known as a Pascal. And 1 Pascal is equal to a Newton per meter squared. So force over some area. We don't use pascals a whole lot. You should kind of just recognize that term. Some other units you might be familiar with. If you own a car, got to fill up the tires, PSI, all right, which stands for pounds per square inch. Now, one of the most commonly used units in chemistry is something known as an atmosphere, abbreviated ATM. And that's kind of basically an atmosphere is defined as one atmosphere is what we exhibit or what is exerted against us, what we feel at sea level. Now, some other common units, and these are ones that I want you to memorize, are millimeters of mercury. That kind of sounds weird because millimeters is like length, and how did we get an element in there? I'll talk about that in a second. And that is equivalent to another unit of pressure called torr. So 1 millimeter mercury is equal to 1 torr. And 760 torr, or also 760 millimeters of mercury, is equal to 1 atmosphere. So I would have these memorized. Now let me talk a little bit about how where millimeters of mercury came about. So this is kind of an old school barometer here. And it's basically a dish filled with mercury, and then there's a glass tube inserted into it. And the way they would measure the atmospheric pressure is um, uh, on a certain day, the atmosphere would press down on that mercury and force it to go up into that glass tube. And they would measure that length in millimeters. And so depending on the pressure of the day, that length, those millimeters might go up or down. And that's where that unit comes in when it comes to millimeters of mercury. Another important property of gases that I want to go into is temperature. Because the temperature of a gas will affect various aspects of it, and especially in its motion. Now, in the past, we have generally used degrees Celsius. You might be familiar with degrees Fahrenheit. The problem is that for gases, this doesn't make sense. Those units don't make sense. And why is that? So recall in the past that temperature is a measure of thermal energy. So a temperature of 0 should represent no energy at all. Okay, but at 0 degrees Celsius or 0 degrees Fahrenheit, molecules are still moving. And so if we're dealing with gases and we put that gas at 0 degrees Celsius, if it were 0, we should see absolutely no movement of those gas molecules. But we know for a fact that they're still moving around. Okay, so molecules, atoms, still have thermal energy at 0 degrees Celsius or 0 degrees Fahrenheit. So this is where we're going to introduce a new type of temperature unit called degrees Kelvin. And we use a capital letter K. And for degrees Kelvin, if something is at 0 degrees Kelvin, that actually means there is no thermal energy, absolutely no movement. In fact, they call 0 degrees Kelvin absolute zero. That's the point at which molecules cease to move at all. There are no vibrations, there's no movement, there's no colliding with containers. They cease to move. And we've gotten pretty close to absolute zero. I don't think any scientists have been able to get down to 0. I think they've gotten to like 0.4 degrees Kelvin. But this is a much more accurate depiction of thermal energy, of the kinetic energy of a gas. So it's going to be very important for you to know how to convert degrees Celsius to Kelvin, because a lot of times the measurements we make in lab, we don't have thermometers that read in Kelvin. We have thermometers that read in Celsius. And when dealing with gases, it's going to be important that you know how to convert that. So degrees Kelvin is equal to the Celsius reading plus 273.15. That's your conversion. So let's kind of do some practice with this. What is the freezing point and boiling point of water in degrees Kelvin? Well, we know that water freezes at 0 degrees Celsius. So to get that into Kelvin, I'm going to add 273.5. So water freezes at 273.15 degrees Kelvin. And water, we know that water boils at 100 degrees Celsius. So I'm going to add 273.15. And so water boils at 373.15 degrees Kelvin. Okay, so to go from Celsius to Kelvin, you just add 273.15. And in a little bit, we're going to start doing calculations. And when gases are involved, you have to use temperature in units of Kelvin.